Okay, so this is chapter, well, it's section 9.1, and this is the introduction to Markov chains. And now this is really the marriage between the matrix things that we were learning towards the beginning of the class and the probability stuff that we've been working on at the end of the class. And the basic idea is that we are looking at things called systems, which have various states. Now, instead of just giving a definition, let me instead just give some example. So, some examples. So first of all, let's consider people in the United States. So U.S. Residents. And these will be our systems. Each person represents a system that can be in various states. They can live, I could literally say the different US states that they live in, but let's say that they can live in urban, like New York City, or suburban, like much of New Jersey, or rural areas. Not supposed to say rural areas. And these are the states, the different possible circumstances in which they can live. And so if you follow one person year after year, maybe they keep living in the city, but maybe they move to the suburbs, or maybe they move out to the sticks, who knows. But the systems are each person, and they can live in one of each of these sorts of states. Let's look at another thing. Senate seats. These are systems. Each Senate seat is a system which can be held by a Democrat, a Republican, or an independent. And these are the various states that each Senate seat could exist in. After 6 years, a Senate seat goes up for re-election. Maybe it's held by a Democrat, but then it gets changed to a Republican or an independent or any sort of switch around. So this is a system where each seat is a system, and who's holding it, what their political party are, the various states that could be in. Here's one where there are a lot of states. Okay, so we can look at an airplane. This will be our system. Can travel to many different airports. And these will be the states, which airport the airplane is in. Okay. So generally the system is some object that we are following around, and the states are the possible descriptions or, of that object. And so, some objects, it could be a person, it could be, an office, it could be a vehicle. The possible descriptions are, where do you live? Who's sitting there? What sort of party is sitting there? What airport are you at? Okay. So, what we're going to be assuming here is we assume that the system changes from state to state by random chance. So we only have probabilities that you move from state A to state B or something like that. And this is something, and I'm just going to write this word down once and then we're not going to use it again, but this is something called a stochastic process, which is the sequence of states that a system follows. So in the example of the airplane, it could be the itinerary. It starts in New York, it flies to LA, then it goes to, so airplane. The stochastic process here could be it starts in New York, then it goes to LA, then it goes to Chicago, then it goes to, I don't know, Boise, whatever, and it keeps going. For the Senate seat, maybe it's a Democrat, and the next year it's the same Democrat, and then he gets voted out, and it's a Republican. She gets voted out, and it's independent. That guy stays there, and then it goes back to the Republican. Who knows? And for a person living in the United States, so a U.S. resident, maybe you're living in the city year to year, and then you decide to move out to the suburbs because you get a family, and then you grow old, and you decide to move out to the rural areas because it might be nice for you. Who knows? These are all stochastic processes, the sequence of states that a system goes by. So let's look at an example, a fairly simple example. So let's say that Verizon finds that 90% of its customers renew their contracts after 2 years. So that means that the other 10% don't. And since everybody has a cell phone, the other 10% go to some competitor. They also find that 5% of non-Verizon customers switch to Verizon after their contracts are up with whatever company they are living in. So here the systems are each customer or wireless user. And the two states that Verizon cares about is whether they have an account at Verizon or they do not have an account in Verizon. So V stands for that they have an account in Verizon. V prime means they have some other wireless provider. Okay. So what do we know? We know that with probability 0.9, somebody goes from Verizon and stays at Verizon. With probability 0.1, somebody starts in Verizon and goes someplace else. We know that 5%, or with probability 0.05, somebody switches from a non-Verizon company to Verizon, and the other 95% stick with a non-Verizon company. They might switch from their company to another one, but not Verizon. Now we can make this all look very nice using something called a transition diagram. Instead of having to draw all this information out like this, I can make things look a little bit simpler. What I'm going to do is I'll draw two circles that represent the two states. We've got people who are Verizon customers and people who are not Verizon customers. Then I'm going to, so I draw circles for each state. Then two, I'm going to draw arrows with probabilities that show the movement between states. So we know that people who stay at Verizon will draw an arrow that starts at Verizon and ends at Verizon, 0.9 or 90% of people start at Verizon and end at Verizon. The other 0.1 start at Verizon and go to somebody else. Now, 5% or 0.05 start at Verizon, and the other 0.95 start without Verizon and end up without Verizon after their contract is up. Okay, so this represents all of this information over here, but in a sort of nice sort of way. You can imagine somebody being over here and coming around this loop and then jumping over here, sticking around with a couple of other providers, then deciding to go back to Verizon, sticking with them for a while, whatever. So it's a nice sort of physical representation of what is going on. But we also represent this using something called a transition probability matrix. This is where getting back to matrices comes in. So a transition probability matrix. Now, since I have two states, I will have a 2 by 2 matrix. So let me just draw a 2 by 2 matrix here, and then I'll describe what I'm doing over here. So 1, I have two states. I will draw a 2 by 2 matrix. Now, each column and row will represent one of the states. Now, what do these represent? The rows will represent the current state, and the columns will represent the next state. That is, after you decide to stay with Verizon or not. Now, I fill this in with probabilities. If this is your current state, let me in fact highlight these things just to emphasize that here's your current state, and here is your next state. Okay. So, what's going on here? What's the probability that somebody starts in Verizon and ends with Verizon? We know that's 0.9. And what's the probability somebody starts with Verizon and ends with somebody else? That's 0.1. Similarly, the probability that somebody starts not with Verizon but ends up with them is 0.05. And the probability that they don't subscribe to Verizon and after 2 years continue not to do so is 0.95. And so what we really did here is we wrote the probability of moving from the row state, by which I mean the state represented by the row, to the column state, by which I mean the state represented by the column. So here's the probability of getting to V, starting at Verizon and ending at Verizon, the probability of starting at Verizon and ending at something other than Verizon. Okay. Now let's suppose that Verizon has, I just made this up, 40% of the US market share. Well, we represent this using something called an initial state the important thing here is initial state, but we could call it an initial state distribution or probability matrix. Now what this is going to be, at least in this case, it will be a 1 by 2, 1 row and 2 column row matrix, and it represents the current state of the market. You can either be a subscriber of Verizon or not, and This says that 40% of people use Verizon, and then the other 60% do not. So the entries equal the percent of people in each state, which is where this word distribution comes in. But you could also think of it as probability, saying that if I would randomly select a person out of the United States, the probability that they have Verizon is 0.4, the probability they don't is 0.6. These numbers are just made up. Okay. Now, if I want to see what is the market share after, a contract period, which is generally, I guess, 2 years, and when I put a dash there, let's pretend that's not there. Well, the way that we might have done this in the past, by which I mean like 2 days ago, is to do a tree diagram. You could either start out a Verizon customer or not, then after one period you could stick with Verizon, or you could move to a different carrier, or if you don't have Verizon you can switch to Verizon or stay with a different carrier. So we're saying that initially 0.4 is the probability you're with Verizon, 0.6 is the probability that you're not. If you're with Verizon after 2 years, there's a 90% chance you're still with them and a 10% chance you're not. If you're not with Verizon after 2 years, there's a 5% chance you'll switch to them and a 95% chance that you do not. So at the end of the day, what this means is, we know that to find the probability that you started with Verizon and stayed with Verizon, so the probability that you started with Verizon and stayed with Verizon is 0.4 times 0.9, which is 0.36. The probability that you were with Verizon and ended not with Verizon, you multiply these probabilities and you get 0.04. The probability that you weren't with Verizon but ended up with Verizon is the product of these two guys, which is 0.03, and the probability that you were not with Verizon and you decided to stick with somebody else is going to be 0.57. All I'm doing is just multiplying across each of these things. That number comes from here. This number comes from here. This number comes from here. And this number comes from here. Okay, so that's where we got these things. But what we're really interested at the end of the day is, if I'm Verizon, I'm saying, well, who has Verizon now? The people who have Verizon now are the people who stuck with Verizon and the people who switched to Verizon. This is going to be the portion of the market that now has Verizon. I add these two guys up. This we've already done with tree diagrams. We say, what outcome are we interested in? Who has Verizon? Well, we add up the ones that have people ending up in Verizon. So Verizon, the probability that you have Verizon after 2 years is going to be 0.36 plus 0.03, which is 0.39. The probability you don't have Verizon, I could just take 1 minus 0.39, which is 0.61, but I could have added that up from the tree. Okay. Well, drawing out a tree diagram each time is pretty tedious, but I would like us to note the following. Let me take my initial state matrix, which is 0.4 and 0.6, and let me multiply it on the right by my transition matrix, which was 0.9, 0.1, 0.05, and 0.95. Well, when I multiply this out, I get 0.4 times 0.9 plus 0.6 times 0.05. And just because I'm running out of room, let me write the second entry down here. The second entry will be 0.4 times 0.1 plus 0.6 times 0.1 plus 0.6 times 0.95. Well, these were precisely, if you go back, this was the very first row, this was the third path rather, this was the second path, and this was the fourth path coming from our probability tree. So indeed, each of these does correspond to probabilities we were looking at before. This is Verizon to Verizon, this is not Verizon to Verizon, this is Verizon to not Verizon, and this is not Verizon to not Verizon. So in fact, this probability here is precisely this guy. This is the 0.36, this is the 0.03, and these will be, corresponding to people who don't, who get up to, or who stick with, don't go to Verizon. So in any case, this is equal to, doing the arithmetic, I get 0.39 and 0.61. Let me not put the question or the comma there. Okay, cool. So this actually gives us a way. So this gives a way of not having to draw the tree diagram. And in fact, it's kind of nice. It's kind of faster. Yes, it involves matrices, but it's a little bit faster. Now from here, we can go and compute more. What about after 2 periods of contracts switching? Well, we can start with the result from 1 period of contract switching, and again multiply it against the transition matrix. 0.9, 0.1, 0.05, and 0.95. That's a 0, not a 6. And this works out to, just do the multiplication yourself, but what this works out to is 0.3815, and 0.6185. I'm having a hard time not drawing these commas here. So I can keep getting, for 3 periods, then I can just multiply this result by this matrix and keep going. This gives me a way of figuring out how many people are using Verizon from period to period. And notice that we started with 0.4, then it went down to 0.39, and now down to 0.3815. So according to this, Verizon is losing market share.